Hey, welcome to our video on proportions and similar triangles. We're going to use proportions in determining some similar triangles here. Hey, looking at the triangle proportionality theorem, it's kind of like a bonus for you, because you already know that these two triangles are going to be similar, right? Without even looking at the triangle proportionality theorem, let me go ahead and just slide it up there out of the way. You have a small triangle, LMQ. You have that small triangle, and let's look at the big triangle. Let's kind of forget about all that for a moment. Well, you know angle L is congruent to angle L. And then what else do you know? Well, you know that those are parallel lines. So these are parallel lines. And so corresponding angles must be congruent. I believe that would be the corresponding angles postulate. And so if you look there, angle makes those two triangles similar. Triangle LMQ is similar to triangle LNP. Okay, so now that we have that out of the way, well, since those two triangles are similar, what else do you know? Well, if I labeled some things here, if I labeled LQ as 15 and QP as 25, LM as 8, and MN as 13. Hold on a second, that's not going to work. Let's go 9 and 15 there. There we go. That's going to work. So if we do this, well, what do you know? Well, look at the small triangle. The left side of the small triangle is going to be 9. What is the left side of the large triangle? Well, it just goes from here to here, right? L to N. Well, that's going to be 9 plus 15. You put these two together. 9 plus 15 is 24. And now let's look at the right side of the small triangle. That gives us a 15. And look at the right side of the large triangle. That will give us 40. So we have large triangle measurements on bottom, small triangle measurements on top. You have the left side on the left and the right side of the triangles on the right. And so if we look here, is this true? 9 over 24, divide each one by 3. I believe we get 3 over 8. 15 over 40, divide each one by 5. You get 3 over 8. So therefore, yeah, that should be true, right? You know the corresponding sides of triangles are going to be, the corresponding sides of similar triangles are going to be proportional. And so therefore, you knew this was going to happen. That's part of the reason why I had to change the numbers over here, so that way they would be proportional. Now you might just say, hey, Mr. Bailey, you made those up. Well, yeah, I might have made those up. But the thing is, these are parallel. And so therefore it had to be numbers that would, because they were similar triangles. Okay, so you've already known how to do this. Now, the bonus that you get today is the triangle proportionality theorem. It says if a line parallel, now you got to remember it's got to be parallel. That means these lines right here have to be parallel. If they're not parallel, then this triangle proportionality theorem doesn't work. So it says, if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. Well, let's go back to our example. We had 15, we had 25. We had 9, and we had 15 here. Well, let's think about this. what the triangle proportionality theorem is telling us is that we can take LM and put that over top of MN. And that's going to be equal to LQ over top of QP. Okay, now remember, this is the small triangle on top. Now this on the bottom is not the large triangle. MN is the left side, that matches the left side of the small triangle, and QP, that's the right side. Those are on bottom. This is what the triangle proportionality theorem will tell you. It says it divides the two sides proportionally. Okay, now you could have gotten by in your geometry without the triangle proportionality theorem. It's just here in a little bit, we are going to be talking about things that, let's see, if you have a parallel line, and a parallel line, and a parallel line, you have stuff like this. Well, eventually these will get to becoming a triangle out through here, but we're looking at that segment and that segment compared to these two segments. So this is why the triangle proportionality theorem is going to be helpful for you in the future. Either way, you can solve, like, say if this was unknown, you can use triangle proportionality theorem, or you can use similar triangles. So this is what we have here. I would like you to prove at this moment that MQ is parallel to NP, and this is, we just have been given some information. I know that this looks like the previous triangle in the previous slide, but remember in the previous slide, these lines were parallel. So what we're going to look at now, we're going to prove MQ is parallel to NP. Well, let me see here. Look at that. It's like magic right there. Alright, so I have, as you can see, LMQ is the triangle. LMQ, I'm going to label this as being 6 and this being as 4. And then so now when we look here, what is the length of LP? Well, 9 plus 6 would make 15. We're not worried about this so much anymore. We're looking at LP is 15. How about LN? How long is that? Well, that was 6 and that's 4, so that makes 10. So therefore we have a 10 and a 15. So you're supposed to be able to identify, like, kind of splitting those two triangles up. That's what you're supposed to be looking at. So if we look here, let's look. Do you see this triangle here? On top of it, when I pull it apart, you will also know that angle L is congruent to angle L. So we have an angle that's congruent there. Now let's look at sides. We have 4 over top of this whole side, LN, which is 10. What does that reduce to? Divide the top by 2 and divide the bottom by 2, we get 2/5. Let's look at the right side. LQ, which is 6. Look at the right side of LP, that is 15. Divide both of them by 3. 6 divided by 3 is 2. 15 divided by 3 is 5. So now, using our triangle similarity theorems, we know that since we have an angle that's congruent and two sets of sides that are proportional, there's a side, there's an angle, and there's the third or the second side. So the two triangles are going to be similar. Triangle LNP is similar to triangle LMQ. And that would be side angle side. Now, remember, it's asking us to figure out that segment is parallel to that segment. Well, what do we know about similar triangles? Well, similar triangles, we know that they have all angles, all corresponding angles are congruent. And so therefore, when I transfer this over to the large triangle now, and I'm only worried about these two angles, since those two angles are congruent, we know that those are going to be parallel. These two angles right here, those two angles are congruent because of corresponding angles. If you have corresponding angles that are congruent, the lines are going to be parallel. I believe that's the corresponding angles, that's the converse to the corresponding angles postulate. And so therefore you've proven that MQ is parallel to NP. So you might think, well, that's kind of neat. It's a lot of fun. I'm glad I'm spending my Saturday night doing this. It's a hoot. But then, it's a theorem. Somebody's proved that a long, long time ago. But now that you know how to prove it, now you know why this is true, why this theorem holds true. This is the converse of the triangle proportionality theorem. It says, if a line divides the two sides of a triangle proportionally, then it is parallel to the third side. So it says, if a line, it's talking about this line right here, it divides the two sides of the triangle proportionally, so then it is parallel to that third side. That's the converse to the triangle proportionality theorem. Okay, we're going to use some of the triangle proportionality theorem right here to find the value, to find the measurement of segment RS. If you feel comfortable in doing this, you go ahead and do this. If you would like to see my explanation here, then we can you can watch. I'm looking right now. Since this is parallel, I know that RS over top of RS is the top side of the small triangle. What's the top side of the large triangle? RT. RS over RT is going to be equal to RV over top of the left side of the large triangle, RU. And so from here we just substitute some values. RS is the unknown. Let me use a variable for that. RT is going to be, what is RT? Well, if RS is X, RT is going to be X plus 30. RV is 12. RU is going to be 12 plus 20, which makes 32. To get RU, you have to add both of those together. Let's do some cross multiplying here. X gets multiplied by 32 to give us 32x. 12 gets multiplied by everything there. So you put it in parentheses and use the distributive property. So 32x is equal to 12 times x, and 12 times 30, I believe, is 360. We're going to subtract subtract 12x from both sides. So 20x equals 360. Divide by 20. Divide by 20. I know the zeros cancel out, so what is 36 divided by 2? 18. Determine the measurement of RS. RS is equal to 18. So there you go. That's using the triangle proportionality theorem. This one here is using the converse to the triangle proportionality theorem. It says determine if segment HJ is parallel to segment KL. Well, in order to determine that, you'll take 30 and put it over top of 48. And that should be equal to 25 over top of 38. Well, looking at 30 and 48 here, this left fraction, let's reduce it. I know 6 goes into both of them. 6 goes into 30 5 times. 6 goes into 48 8 times. And then looking at 25 over 38, what number goes into 25 that also goes into 38? Well, 38 breaks down into 19 times 2. And I know 19 does not go into 25, and I know 2 does not go into 25. 25 over 38 is the reduced form. So are these two fractions equal? No, they're not. So let's go back to our question. Determine if these two segments are parallel. They are not parallel. And they're not parallel because those two fractions are not equal. You could have also, I'll just show you a real quick way. You could have put, let's see. You could have taken left side of the small triangle and put it over top of the left side of the large triangle and determined right side of the small triangle and right side of the large triangle. 25 and 38 make 63. 63, yeah. And determine if those two fractions would be equal. 6 goes on the, we're going to reduce this by 6. That reduces down to 5 over 18. And 25 over 63. 63 is 7 times 3 times 3. 7 times 3 is 21, times 3 is 63. And none of those factors, 7, 3, or 3, go into 25. So 25 over 63 is also reduced. This is just a different way of looking at it. You can either use the individual parts, 30 over 48, or you can use 30 over the whole side of 78. Try to reduce. But it all boils down to they're not equal, or they're not parallel. If they were parallel, those would have to be equal. Using the triangle proportionality theorem, okay, these are parallel, so therefore that should tell us some things. I would like you to find the value of A and B. Go ahead and pause the video, and then when you get done, you hit play and check to make sure that your work matches mine. Just to clarify, that length of 40 is the whole segment. That is V. That wasn't a very straight line. That is VY. That segment is 40. So go ahead and see what you can do. All right, I'm looking at, let's look at B. We know that since these are parallel, we can set 7.5 over 12.5 we can also set, since 7.5 is part of the small triangle, 5 is part of the small triangle. And 12.5 is down here. B should also be down here. Now here's the thing. B is part of the large triangle, right? 12.5 is just it's not the whole side of that. So that's the reason why down here, when I have 12.5, I have to change that. I can't leave it as 12.5. Because this is part of the large triangle. 7.5 and 12.5 make 20. And so 20 now is that whole left side of the triangle, and B is the whole right side of the triangle. And these are part of the large triangle. These are part of the small triangle right here. There we go. Now that we got some things straightened around, we can go ahead and do some solving. Let's do some cross multiplication here. 5 times 20 is equal to 7.5 times B. 7.5 times B. 5 times 20 is 100. 7.5B. And how do we get 7.5 away from B? We're going to divide. So now B is equal to, well, since this has a decimal, we want to get rid of the decimal so we can reduce. Let's move the decimal one place to the right, which means we also have to take this decimal and move it one place to the right, fill it in with the 0. And so now we're really looking at this fraction right here, 1,000 divided by 75. I know 25 goes into both of them. It goes into 75 3 times. 25 goes into 1,000 40 times. And so therefore B is equal to 40 over 3. If you need to, I usually don't need you to change it to a mixed number. 16.67 or 16.6 repeating. You have to read your directions to figure out what it wants for your answer. But I'm okay with this, 40 over 3. Alright, so that's letter B. Now we have to find letter A. Let me get rid of some of this work here. Letter A. Letter A. Letter A is right here. So if Z to Y is letter A, what is V to Z going to be? V to Z, the whole thing is 40, and we take this part out of 40, so 40 minus A leaves us with VZ. And so that's where we're at. So let's go ahead and solve for A. 7.5 over top of 7.5 over top of, we're going to put it over top of 12.5. The triangle proportionality theorem says we can break it up like that. It says that we can take this small part here and this small part just because those are parallel. And then from here we have to say if 7.5 was on top, it's part of that. 40 minus A will go on top. And then down on bottom, this part right here, letter A. Let's do some multiplication. 7.5 times A, that's equal to 12.5 times all of that. I don't know why I put the decimal point there. There we go. Now let's do some multiplication for you. 12 times, wow, 12.5 times 40. That's going to be 500. And 12.5 times negative a is negative 12.5a. How do we get a by itself? We're going to add 12.5 to both sides. Leaving us with 20a is equal to 500. Divide both sides by 20. I'm going to cancel off the zeros, so 50 divided by 2 is 25. So a is 25. And so now once we get rid of some of this, remember that this one was 40 minus a. So if a is 25, 40 minus a, which is 40 minus 25, that is 15. 15 and 25, does that make 40? We've done well then. So looking there, you found both A and you found B. This theorem here is, you can kind of imagine if we were to extend these and we were looking, you know, forget about all this here. We're just looking. This right here should remind you of the triangle proportionality theorem. You have a triangle, and then these two lines right here are going to be parallel. Well, the thing is, this theorem that we're talking about deals with if three parallel lines, and this also works with you have more than three parallel lines. So if three or more parallel lines intersect two transversals, then they divide the transversals proportionally. What that means is this distance, AB, over top of that distance, DE, is equal to distance BC over top of EF. And that's what it means. It divides the transversals proportionally. This is kind of handy if you're setting up a city. Burgundy Street, Dauphine Street, Royal Street, Franklin, Spain streets. Sounds like a fun time. I'm just trying to figure out what's down here at letter A. So what is the distance from point C to D? So what is this little distance right here between those two streets? Maybe Burgundy and Dauphine? Well, you have to look at the other measurements here. We will assume that the city directors that set up this program wanted to make these streets to be parallel. Because if they're not parallel, then they all come crashing in together at some point in the middle of town. Causes some headaches. So if we look, how do we set this up? Let's label that as X. So we're going to take 150, which relates to X. And then we're going to take 250, which relates to 960. Now, anytime you can reduce some fractions, you should probably go ahead and do that. I'm looking right here at 250, 960. I divided both of those by 10. So when I divide both of those by 10, I get 25 over 96. So from here, we're going to do some calculations. Let's go ahead and do some cross multiplying. 150 times 96 and x times 25. So 150 times 96 is going to equal 14,400. And when we divide by 25, x will then equal 576. And so the distance between Burgundy Street and Dauphine Street are going to be 576. In the last theorem for this section, it says if a ray bisects an angle of a triangle, so we have this ray bisecting the angle right here, then that ray divides the opposite side into the segments whose lengths are proportional to the lengths of the two sides. And so you can see here, it says A over B is equal to C over D. And that's only if this ray is the angle bisector. And so when we compare it to something like this, we have a ray that is the angle bisector. So 14 over 21, that's equal to, since 14 was on top, x goes on top, over 9. Like I said before in the last slide, 14 over 21 reduces to 2 over 3. Always reduce, that way it makes your multiplication a little bit easier. So now 2 times 9 is 18, 3 times x is 3x. Divide both sides by 3, x then equals 6. And so you have the value of x is equal to 6. This next one here is a little bit more challenging for the simple fact that it uses some of the stuff that we've already used. If we look, first off, we have a ray that is the angle bisector. And so from here, if the whole thing is z, what is this part? Well, it is 9 minus z. And so now we're going to go 12 over 15. And since 12 went on top, z will go on top. And then both of those are on bottom. 9 minus z. 12 over 15, 3 goes into both of them, leaving us with 4 over 5. And now cross multiply. 4 times 9 minus z is equal to 5 times z. Solve this out. Should get 36 minus 4z is equal to 5z. We're going to add 4z to both sides, leaving us with 36 is equal to 9z. So from here, divide by 9, z is equal to 36 divided by 9 is 4. Z is equal to 4. We could plug that back in. Since z is equal to 4, this must be equal to 5. So find this 4 over 12 is equal to 1/3. 5 over 15, that's also equal to 1/3. So that's one way you can check to verify your answer is correct. Z equals 4. Appreciate you guys stopping by for this lesson. We will see you the next time.
I'm